today to talk to you about flywheels. What exactly is a flywheel? Some of you already know from past experiences, but you may not know how broad the definition actually is. Whether you don't know what a flywheel is, or you have a minimal view of what all involves a flywheel, if you're like most engineers, the number one place you go is Google. The definition of a flywheel is basically broken down into the definition of an energy storage unit used to keep motion smooth. But what are some components of a flywheel with this definition? We know energy storage, but how? This is done through inertia, as seen as with the tethered tennis ball example we've all seen in physics class. As seen in this figure, flywheels do not have to be uniform in mass, but still contain key elements. Inertia requires mass and a distance, which causes velocity, either linear or angular. Benefits of flywheels is the added energy caused by this inertia. This causes an even power distribution. Negatives come from the inertia required to start the turning of this flywheel. This causes a less efficient process and a slower acceleration. Since the added mass is a key component in flywheels, this might not be applicable for situations such as aerospace, when mass needs to be minimized. To show this graphically, we have torque output over time in a 4-stroke engine, with and without a flywheel. As you know, the only time power is produced in a 4-stroke engine is during the power stroke. In the no flywheel case, this is shown in minimal torque output in all other processes and a large delta in the power, seen in the bottom graph here. In the with flywheel case, the energy storage of the flywheel is used during the other strokes of the engine, thereby decreasing this delta during the power stroke and increasing the torque output in all other locations. To really visualize this graph, we're going to take a quick break and look at a YouTube video, one with a regular flywheel and one with a modified flywheel. As you see, in the modified flywheel case, mass is decreased and the acceleration is increased. The next parts of these lectures, we will discuss applications in which flywheels are used. We will go over example problems, and we will discuss failure modes of flywheels in various applications.
Okay, so we got a couple of different flywheels here. This flywheel here is an iron flywheel out of an automotive application. This is nodular iron. This is nodular here. Also on the back here, nodular. So this is it's a cast piece that's machined. Flat surface here is where the flywheel bolts to the crankshaft. It's a 6-bolt square pattern. Can go on any direction. There's no external weights anywhere on the flywheel, so it's not a directionally balanced component. Ring gear around the outside here is for the starter motor to engage with. On the mating side here, if this wasn't rusty, this would be all nice and shiny. This is where the clutch disc rides. And then there's 3 dowel pins here that the pressure plate sits on top of. And then the pressure plate bolts with 6 bolts to the flywheel here. And then there's a throw-out bearing that actuates the clutch. Anyway, the idea here is that this is heavy. This is 20, 25, 26, 27 pounds. And it was replaced with a very lightweight aluminum component. It was an aluminum version of this that had a steel insert for where the clutch disc rides. That aftermarket replacement weighs something on the order of 12 pounds. So being that it was lighter by basically half, it's got much less mass, a lot less inertia. So as you saw in one of the other portions of the video, it speeds up faster or it accelerates faster. There's a performance component that comes along with that. The degradation or the downside of that is that in a car application, when you try to take off from a stop without having that extra mass of the flywheel, it can take a little more throttle or whatever and a little more clutch slippage to get the car moving. This other flywheel here, this is just a small engine flywheel off of a go-kart, like a racing go-kart. It's an aluminum piece, not very heavy. Has a few magnets integrated into it. This thing goes on the end of the crank, and as it spins, there's an ignition coil that sits on top of this with an air gap. And as the flywheel spins, it triggers the coil, which creates a spark that goes to the spark plug, and that's your ignition point. Anyway, this has got a plastic fan that's bolted to the flywheel. On the engine, there would be in stock trim anyway, there would be a fan housing, and this fan blows air across the motor because it's an air-cooled application. There's a taper on the inside of this hub. Probably can't see it, but that taper matches up with the taper in the crank. This just happens to be a crank that goes with this. So there's a taper on the end of the shaft here, and that taper indexes with the taper on the flywheel, and then when the nut goes down to hold it all in place, it locks in place. It's called a wedge mate or a locked or an interference kind of a fit. There are a couple of keyways on both of these parts. There's a keyway in the crankshaft, and there's also a keyway in the flywheel. The keyway, however, is not a component of keeping the flywheel on the crank. The keyway is strictly for setting the ignition timing. I'm not sure if this shows in the video, but the keyways would get lined up. There's a soft metal key that goes in here, and that sets the ignition timing in relationship to the crankshaft. But it's this taper surface and the taper in the flywheel that get actually locked together to mount the flywheel onto the crankshaft.
Other applications that use flywheels include sewing machines. As a force is given to the bottom pedal, the flywheel rotates, while the small wheel works as a pulley. Even when force is not exerted to the foot pedal, the large wheel works as the flywheel and continues rotating through the inertia of the flywheel. This can also be seen in children's games such as a tap and a toy car. New to the market are fidget spinners. These work the same way as flywheels due to rotating through inertia. To begin our flywheel example problems, we'll start with a very basic problem, just so we understand all the terms. Our first example reads, a flywheel of mass 182 kilograms has a radius of 0.62 meters. What is the torque required to bring the flywheel from rest to a speed of 120 RPM in an interval of 30 seconds? First, we begin by writing down our knowns, as always in example problems. Some assumptions include that our flywheel is a uniform hoop, and this is a basic sketch of what we're talking about, again with that simple angular velocity. Radius is known, and our time interval. We also know mass as well, which is not indicated in the sketch. From there, we can solve for our change in rotational velocity, and we also convert to radians per second. From there, we can use the relationship to solve for torque, being radius times force. From there, we can use basic substitution rules, because force is mass times acceleration, but acceleration in the second equation is linear acceleration, and we are working in angular. So we can substitute again, and we also have to note acceleration and velocity are time derivatives, so we can again substitute in what we already know with basic equations, and we can solve for our answer, since we already know all of the variables in this equation. So that was pretty simple, But do we really understand what this relationship means? So some simple questions would be, what would happen to torque if we increased or decreased this mass? What would we do to increase the time it took to stop the flywheel from rotating at 120 RPM? And what would the amount of torque required to bring the same flywheel as this previous example to a stop be the same time? Would it be a larger time, a less time, or would it be the same? And now we can move on to a more complex example since we know the terms a little bit better.
Okay, we've got a flywheel example problem here that we're going to work through. So the flywheel section in the text starts on page 858, and it is a whopping 5.5 pages long. There's one example worked here and a handful of equations. And then at the back of the chapter there's one example problem, or one practice problem, and that happens to be 1623. So that's what we're going to look at. So the problem statement says that a cast iron flywheel has a rim whose OD is 1.5 meters and whose ID is 1.4 meters. The flywheel weight is to be such that an energy fluctuation of 6.5 J will cause the angular speed to vary no more than 240 to 260 revs per minute. Estimate the coefficient of speed fluctuation, and if the weight of the spokes is neglected, what should the width of the rim be? So I found a drawing here. This is a flywheel. Obviously these are the spokes and a hub. So really the only part that we're interested in is this outer rim. So we have the outside diameter, or the large D, the inside diameter, or the small d. So these are the 1.5 and 1.4 meter diameters. And then the width of the rim I've actually got listed here as an h. So this is a height in my mind. So first we're going to find the coefficient of the speed fluctuation, which is characterized as a c with a sub s. So your omega 1, or your speed 1, was given in the problem statement at 240 RPM, and the omega 2 is 260 RPM. So to start, we need to find the nominal angular velocity, which is just the average. So we're going to take the 240 first speed and plus the 260 second speed divided by 2. We end up with a nominal angular velocity of 250 RPM. This is from equation 1663. The equation for the actual coefficient of speed fluctuation is equation 1662 in the text, and that equation says that omega 2 minus omega 1 over the omega, or the average value, gives you this coefficient of speed fluctuation. So plugging in the numbers, we end up with a value of 0.08. So the second part of the problem asks us to find the width, or in this case the height of the rim. Bearing in mind again that the large, or outside diameter, is 1.5 meters and the inner diameter is 1.4 meters. So we have to convert the nominal angular velocity from an RPM to radians per second for the equations that we're going to be using. So as a reminder, radians per second, or I'm sorry, RPM to radians per second is 2 pi speed in RPM over 60. So plugging in our 250 RPM number for omega here, we get 26.18 radians per second. The 6.75 given in the problem statement is this E2 minus E1 value, and what they're saying here is that the energy fluctuation is going to be 6.75. So E2 is the kinetic energy at state 2, E1 is the kinetic energy at state 2, or I'm sorry, at state 1. So all we're saying is that the difference between those two is the 6.75 J number. And again, E1 and E2 represent the kinetic energy at each state, and you can do some math to calculate these values. Those equations are given as equations E and F on page 859. So the equation that we're going to use here is this E2 minus E1 is equal to CSI omega squared, 1664. So we know E2 and E2 minus E1, we know CS, and we know omega. So we're going to rearrange this to solve for this I value. So rearranging that equation to solve for I, we're going to get the E2 minus E1 over CS omega squared, 6.75, the 0.08 CS factor, and this 2618 squared. That solves to 123.11 newton meters per second, or newton meter seconds squared rather. Out of table A18 at the back of the book, we find that I is mass over 8 times the outer diameter squared plus the inner diameter squared. Again, we have the I value from right here, this 123.11. We know the large diameter, the small diameter, so now we need to solve for m, which in this case is the mass. So again, rearranging this equation here, we get mass is equal to 8I over the OD squared plus the ID squared, which gives us a mass of 233.94 kilograms. So in order to solve this problem, what we really need is to figure out what the volume is. Volume is going to help us find the height or the width here. So the weight, or unit weight of cast iron per cubic meter is given as 70.6 kilonewtons. To find the density, we're going to take that value and divide it by gravity, and you end up with a density of 7196.7 kilograms per meter squared. Volume, as you recall, is mass over density. We know that the mass is 233.94 because we calculated it above. We just found the density of 7196.7. So it's going to give us a volume, total volume of the hull, or the rim of this flywheel, as 0.0325 cubic meters. You may recall that the volume of a hollow cylinder is basically just pi outer diameter minus inner diameter, both squared, over 4 times the height. So this is where that width comes in from the beginning of the problem. So this is h. This is what we're really trying to find. So we're going to take that equation and rearrange it to find h. So h is going to be equal to 4v over pi times the outer diameter squared minus the inner diameter squared. Plug in all the values that we already have. So v, again, we just calculated as 0.0325. We know that we've got an outer diameter of 1.5 and an inner diameter of 1.4, and that solves to basically 143 millimeters. So what we're saying is the width, or the height, of this flywheel is 143 millimeters. So not a lot to this. You kind of have to think about it to understand what they're asking. Figuring out this volume component to solve for the h took a little bit of thinking, but there's not a lot here, so that's how you do it.
Failure methods of flywheels are few and far between, since they are really only just a mass rotating. Failure methods of flywheels mainly come from how they are attached to a shaft. As seen in this picture, the flywheel is attached to the shaft through the use of a key. If this key were to break, the flywheel would not stay on the shaft, and rotation would be hindered. One way a flywheel itself could fail is through wobble. Wobble is when the mass of a flywheel is not even across the entire symmetrical plane. This causes one part of the flywheel to be heavier than other, creating an uneven rotation. This uneven rotation can lead to major stability problems at certain speeds.